So I'm going to do a question from LeetCode. It's called list. So this question is also on Gigs for Gigs. On Gigs for Gigs, it's called list common ancestor of a binary tree. Yeah, and on LeetCode, it is also called lowest common ancestor of a binary tree. So on LeetCode, this question is question number 236. Lowest common ancestor of a binary tree. All right, let me go ahead and read the questions. So given a binary tree, find the lowest common ancestor, LCA. So LCA of two given nodes in the tree. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T that have both P and Q as descendant, where we allow a node to be a descendant of itself. Given the following binary tree, so to give us an example, let me find a ruler. Yeah, so tonight I want to go sleep early. So random, but getting 8 hours sleep is really good. Just fun fact. So according to example 3, 5, 1, 6, 2, 7, and 4. So since I'm doing this to prepare for my interview, and during the interview, the interviewer expects you to ask more questions, or maybe the interviewer doesn't even give us any input at all, any example at all. So I need to ask the interviewer for a couple of example. So in this LeetCode, they provide us an example. So the example that they give us is when P is equal to 5 and Q is equal to 1, and the output is 3. So lowest common ancestor of a binary tree. So alright, so we need to identify the key term. What does it mean by lowest common ancestor? So lowest so there's a lot of terms that I need to understand. What is the descendant? So what is a descendant? I read in a book, that's the element of programming, whatever that is. It say that descendant is basically, I mean, 1 is a descendant of 3, 5 is a descendant of 3. So descendant is mean that your child or your grandchild, because 1 is a descendant of 3 and 5 is a descendant of 3. 6 is also a descendant of 3, and 2 is also descendant of 3. But 8 is not a descendant of 5. So descendant is basically a child relationship, if you think it that way. So what is my strategy of solving this? So lowest common ancestor is basically refer to a node that connect two nodes, like node P and Q, closest. Basically, the closest node the shortest node that connect node P and Q. So they give us another example when P is equal to 5 and Q is equal to 4. So in this case, the output is 5 because it's saying that phi is a descendant of itself. So phi is a descendant of phi. So, okay. I wonder if oh, okay. I think I said something wrong, incorrect earlier in the video. I think 4 and 0 have a closest descendant as 3. Like the lowest common ancestor. Let's see. Let me try it on the LeetCode console. So in the case of 4 and 0, so like this would be like something you want, or I want to ask the interviewer like what would be the output if the value of P is 4 and the value of Q is 0. I think this is a good question. So expected 3. So expected to return this in case that P is equal to 4 and Q is equal to 0. And other thing that I can answer is like what is the data type of P and Q? So on LeetCode, P, so what are the given inputs? So according to LeetCode, the given input are root, P, and Q, and all of them have a node type. So there's a node like on LeetCode. Say all of the nodes value will be unique. P and Q are different, and both value will exist in the binary tree. Oh, yeah, that's like something that I should ask to clarify. So is it like guaranteed that P and Q will be like in the tree? So is P and Q I think are P and Q guaranteed to be in the tree? Yes. So I have P and Q. So we have some area here. I mean, we can always like do a brute force. So, like another way of thinking about lowest common ancestor is we think of if there is any like possible path that going from this node to the descendant. So it's like in the case of 4 and 0, in this case, we can go to 4 and 0 through this, and 2, 0 through this. So this is like the only like ancestor that connect these two nodes. However, so in the case of in the case of 0 and B, the ancestor ancestor that connected two nodes like 0 and B would be 1. But 3 also like connected to ancestor as well. You know what? We can always like do brute force. So what do you mean by brute force? So basically we start like from top. And then we traverse. So it's always guaranteed that we can find those two nodes. So we just like traverse left, left, right, left, right, right. And then left. So basically we have so we need to have like some sort of way to like passing the information to all this node, like to count how many steps in order to get there. So we can just like start at level 0, level 1, level 2, and level 3, and level 4. So for example, in the case of this, P is equal to 4. So we traverse. So we should have like some sort of dictionary that represent like all of the nodes in this tree. So initially, like node 3 require 1, 2, 3 require like 3 steps. To get there, and it require 2 steps plus 2, so it require 5 steps. And then we look at node 5. So node 5, we traverse left, right, and we found it. So we stop recursing, and then we found 4, right? Then we do like 3, and then here, and then we traverse to here, and we couldn't find it, so plus X. So this is not plausible. So this is wrong. Then we traverse 1. So this is like null. And we traverse 1, and then we see that so we found 0, right? So it take just like 1 step. And then we plus nothing, so it's null. Okay, get some sort of hints. So it's like when we found like left and right child, so 3 have 5 as a left child and 1 as a right child. Once your left and right child are null, we can just stop and return this value, which is 5. And we also need to return the node. There's supposed to be a node. No, node 3. This node. This is not node. This doesn't have to be a node. So we traverse. So we traverse through it. So we traverse through the tree. And so in the case that we found, like we got the result. That's cool, that's good. So in case that we found the result, that's good. But if not, if both of left and right child, I think my example is a little bit too complicated. So let's think small. So ideally, root is a common ancestor to every other node, but it might not be the lowest common ancestor. So let's look at a closer example. Let's see. Have A, have B, have C, have D, E. So if we look at the least common ancestor between D and G. So first we start with A. We can verify that we can find D. So D take about 0, 1, 2. So for A, it requires to go 2 plus 3. So we get 5. And then we look at B, so we traverse, and then we couldn't find G. So let's say P is equal to D, and Q is equal to G. So for B you couldn't find. C we couldn't find either. So since we couldn't find like both P and Q and the children, we just prematurely like stop the program right here. So how about the case when we have I don't know, let's say our P is C and this is G. So we look at A, so we can find our P and our G. And then we look at B, we couldn't find it. Then we look at C. So C, first we found it, so that's basically just right here, so it's just like 0. And then it found another 1, so 1, 2, so +2. So this is good. And then we explore to F. Oh. No, we do E, we couldn't find it. We do D, couldn't find it. No. So once we are at C, we want to explore the child of C. But we couldn't find C. Right here we can only find G since two children of C cannot find C and G, we just like prematurely like stop the program and return C. Can I do better than this? Maybe, maybe not, but let's think. So what is my strategy? Let's write some like pseudocodes. So my strategy is I think on the last video I didn't discuss about time complexity and space complexity, so I think I will do that analysis on this one. So traverse from root and traverse on left child and right child. If left child and right child can find P and Q, stop. And return parent nodes. Traverse on L child and right child. If left child and right child can't find P and Q, stop and return parents nodes. So we assume that parents node containing both P and Q. So it's like if we look at this example, like when we have D and G, so we start at this node, like our stack is on top, so it's reverse, go left, couldn't find it, go right, it's found it. I don't think we need to keep track of this value. We're just saying that once we couldn't find it, we just stop. Once both of our children doesn't contain PQ, we just return the parents. So like right here, we start at the stack, so we traverse through and then we found D. And then we also like traverse through here and we found G. So this is good. So, and then we want to check our left. So since our left child couldn't find it, it returned null. And since this couldn't find it, it's also returned null. But we need to be careful. When we check, we need to check ourselves too. In the case that the input was A and G. So we need to check the parent itself as well. So this is recursion again. This is recursion. But the idea is, first we need to check the nodes, and if the nodes containing both P and Q, we want to return that nodes. If not, we want to return null. And in the case that no, we don't want to return that node yet. We only return that node if the children is not good. If the children couldn't find P and Q. Alright, let's test the example. I like testing more than writing codes. But let's try one more time. 3, 5, 1, 6, 2, 8, 7, and then let's say P is equal to 5, Q is equal to 1. So we given this, and so this is like straightforward. So first it checked this in the stack, so it traversed through here, so it can find 5, right? And it also traversed through here, 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 and it's traversed to here. So this is one, it's found like those two, it stopped and go up here, and then it recurs on 5 and it try to find, so it could find P itself, but it couldn't find Q, so it returned null to the parent, and 1 couldn't find 5, so it returned null as well. But what is the time complexity of doing this? So this would, so like just like the parents itself would be ON, this would be ON over 2, and this would be ON over 2. But what if there was like a worst case? So like in this case, we will eliminate like half. What is the worst case of this example? It's difficult to come up, but I think it's not ON squared, because let's say that P is equal to 2 and Q is equal to 4, and we have like many over here, right? So in that case, it will traverse this ON of time. So check the left. So like 1, it find this. Let's say that 4 is like, for some reason, it's like up here. So if that was the case, so it would check here, it found here, and it's found here. So 3 will find, so 3 will find 2 and 4. 5 can't. 4 can't. So it's only traverse like 2 times. Like 2 ends. let's say that if P is equal to 10 and Q is equal to 100, this would be, so it traverses through here. Can find it, yeah. Traverse through here. Can't find it, so it stopped right here. So stop. Right, traverse through here. And can find it. So since it's can find it, so it's going to traverse through here. Cannot find it, so it stopped. And then it traverses through here. Then it traverses through here, could find it. Say 100. Then it traversed to here, so it couldn't find it. Couldn't find it, so it just returned the parent 10. Then we'll return to here, return to here, and return to here. Where's the worst case? If it was a linked list, what would be a worst case? Say P and Q. Oh, that would be the worst. So it's start here. It's say, oh, okay, I see something. So let's say it's like right, and this bro said, yeah, I see something as well. So it's keep going down. Oh, I see something. So this would be O(n) square. Can I do better? Maybe. So it would just say P is the lowest common ancestor. I think I might be able to come up with like a better solution if I think a little bit more. Let's write pseudocode for this one. So let's call this check current node if it could find P and Q. If not, return null. Else, so else it means if it could find P and Q's, traverse left and right. If left and right can find P and Q, return current node. If one of them can find I think in Python it's allowed you like to do like OR. So if we can do like OR A or B and OR null, so return A. All right, let's try to write the code with this pseudocode. All right, here's my ruler. So let's call function main. So we have root another question that I can ask is whether P and Q are like the same node. So in the case they are the same node, it would just be one of like P or Q, like so we need to return. And then if root you want to call meow. My roommate's cat is meowing. He's waiting for my roommate. All right, let's try the recursion function. Oh, it's also need to know P and Q. So if, according to my pseudocode, so if current node if nodes, so if it's valid, I think I need to have another function that check the validity of this. Okay. So if nodes, so in the case that it's not, if it's not a node, I just want to return no. And then so like this would check if the node contain P or Q or not. So let's say that this valid does the job. So this will return true or false. So if valid nodes P and Q, we want to recurse our child. So we have to do recursion node. We want to save this information. Temp. node.left P and Q. Temp2 recursion node.right P and Q as well. So I will recurse that. Is there any case that both temp1 and temp2 will return a node? Interesting. So I mean, if we look at the picture, let's say right here, A, B, C, D, E, F, G, H, I. Let's say I and G. Let's say A. Let's say I and E. So this valid, it's valid, it's not valid. So only one children that could have like a valid, not both of them. So I guess I can do, I think we can do return. So we want to return the child first because like the child is like the closer. So we want to return the child, which is temp1. Alright, let's walk through the solution. Just say that this will do its magic for you. So in the case that P is equal to let's say P is equal to I and Q is equal to E. So first thing is like we go through A, so we call recurse on A. P and Q is I and E. There's two lovely nodes. And nodes right here. So since this one is I thought it's true and false, so I think just return node or null. Nodes are null. So if it's true, return nodes. If it's false, return null. Alright. So A, it's checked, and then since it's checked, it's valid. So this is can just like initialize temp1 is equal to temp2 up here equal to null. Right. So then temp1 call recursion, so which is this one. So when it's called recursions, it's also a valid node. And it's called this, but this is like invalid. It could only find I, but I couldn't find E. And then you call this one. It couldn't find I. It couldn't find I, so this is like null. So both of this like null, and it will return just B to the top. And then over here, we call like recursion on this, and I couldn't find it, so this is like null. And then we will get, so right here we will get B, and then null, and then A. So it's going to return B, which is right. Yeah. Now I guess let's go with one more time, like slowly. I'm a little bit confused. So P is I and E. So initially we go A, like this is our main stack. So A is the node, so it passed this, and then wallet, so it's ticked. So in the case that it's not wallet, it's just return null. But this is wallet, so it's called temp1. So temp1 go up here, so it's a node, and then itself it is wallet because B containing I and E. So it recurs on this one. When it recurs on this one, it's invalid, so it's going to return null. And this guy also return null because temp2 right here couldn't find it, so it's going up here, so right here, so it's going to return null, and the node, so it return B to the right here to temp1, and then temp2 it's return null, and yeah, so it should work. So now I need to just like working on the wallet function. So for the wallet function, I need to traverse left and right. I think I just need some sort of variable to keep track if I have found P and Q. So I think I need to pass another variable. Let's call that variable like count, like C. Let's pass like, and let's say it's 2. So first we just need to check if, so first we like in this case, let's say like this node is passed, right? So if node is not null or none, we'll do something. Sorry, I want to go. Alright, so let's say if this is the case, so we want to go left, left, left. So first we need to check if it's not none. I think we need to pass this and solve like an object. So this is like a list of 2. So if node is not equal to none, we check the node itself. So in this case, we check A. So we check if node is P or Q. So if it's true, we do and then we also need to recurve left and right. So if, let's call node just n dot left. That is not null. I want to recurse do n dot left. Same thing with the right. You need to do wallet. You also need to pass like P and Q, and then our C. So like on the mainframe, we just need to check if, so if C of 0 is equal to equal 0, return nodes else, return none. Alright, so let's test it. All we need to test. We need to test our code no matter what. Testing is very important. So in the case of I and E, in the case of I and E, I think we only need to do this. We can modify this if it's null, it's none, and C of 0, it's not 0. So in the case of A, we start with A, so A is not, and P and Q is I and E. So initially C of 0 is 2. So we check A. So this is, we don't subtract this at all, and then we traverse left, and then we call on valid. So now our stack frame is like on this, and then so since it's B, so we don't subtract this at all, and then we go left and we go right here. We go left again, so and then we go left again, and then we found D. Since we found D, we subtract this by 1, and then we traverse left and right, and then B right here is traverse right, and then it found it. So since it found it, it subtract this to 0, and then it check left and right here. And since there isn't any, it's just go back. And so let's go back to the top right here, and then it traversed through here. Go F, couldn't find it, so, and then we checked on the stack that C0 is equal to 0, so we return A. Yeah, this is correct. Alright, I think I'm going to end the video right here. It's been like an hour already. I'm going to test it some more and see if this test pass. I think I have like some trouble understanding like passing the counter here. It's a bit tricky. I need to work on it. Like think how would I like passing like the return. There's a lot tricky when they do like recursion, especially with the return value, because you only care about the return on the top level of the stack, not on like the lower level. Like the lower level is just like basically just to modify this value. Or maybe I can just return that value, I guess, instead of like doing this. Alright, I think I'm going to end this video. It's been like an hour already. Alright, bye. Thanks for watching.